Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students, welcome to another class. This time we are looking to continue the material. Hi Sunny. So
Yeah, and
continue with the current electricity material. Last class we looked at the ideas around how Ohm's law, which basically tells us that voltage is directly proportional to the current, and there's a straight line relationship between the two. And then we looked at the idea of resistance. So today I'm going to kind of run through a lot of material. The but to start with, let's go back to what we discussed. Okay, see, drift velocity is defined as the velocity of motion of charged carriers inside a solid, typically a conductor. Okay, now if the motion is very random, right, then the drift velocity is kind of zero. But if there is an electric field which is caused when there is a potential difference, right, then the drift velocity rapidly rises and it is not equal to zero. Okay, so we introduced firstly this idea of J, current density, which is a vector, and we said that the current, which is a scalar, is got by the dot product of J and ds, and then we derived the drift velocity as being the related to the current density, right? And that's basically Ohm's law. V is equal to IR is Ohm's law. J is equal to E N VD is another way of stating it. So direction of current is the direction of flow of positive charge. Okay, so electrons flow up in the opposite direction, right? The direction of flow of current. Okay, so in the presence of an electric field, electrons are accelerated, right? And there are of course some electrons go in the opposite direction. They are very, very, very small and very slow, right? But along the direction of the field, you have when you go against the grain, it's always difficult. When you go up the slope, if you're a fish trying to swim against the current, it's very difficult. Go with the current, you go really fast. That's the analogy in water. So this is no different. Okay, so the time between consecutive collisions is called as the relaxation time. Okay, and so we can calculate the J is equal to NeV. N is the number of electrons in the medium. E is the 1.6 to the power minus 19, and Vd is the drift velocity. Okay, so number of if you have a mole, then you can correspondingly calculate the number of electrons. So the number of electrons in 1 meter cubed, right, is so many. So the number of atoms is so many, right? 6.023 into 10 to the power 23 is the Avogadro number, is the number of electrons in number of atoms in 1 mole. So if you took 1 mole of Cu, right, it will have this many electrons, right? So so total number of atoms in this many moles, right? So is so if you had a density of 9 to 10 to the power of 3 kilograms per meter cube, so how many moles are there? How many atoms are there in that, right? So there are roughly 8.5 into 10 to the power 28 atoms per meter cubed. That's a lot of atoms, right? So that is N. Okay, number of atoms per meter cubed is N, right? So J is so now once you get the number of atoms per meter cubed multiplied by E, which is 1.6 to the power minus 19, times Vd, which is the drift velocity, And that will give you a very clear idea of what the current is. Okay, so there's another way of saying V is equal to IR in so many words. Okay, so now in the case of thermal speed, right? In the case of thermal speed, you have from the kinetic theory of gases, 3/2 kT is equal to half mv square, right? The average speed of is given using that, right? But thermal speed is through the conduction of heat, right? Now, typically, thermal speed is very low compared to is very different compared to the speed in the context of drift current, or it's the other way around. Thermal speed is now current density is defined as the current per unit area, conductivity and conductance. Conductance is defined as the ease of flow of current of charge carriers through a conductor. Okay. Now, conductance is the inverse of resistance. 1 by rho is the conductance. Okay. Conductivity is specific to the particular material. So copper will have a conductivity, etc. Okay. Now, Ohm's law states that J is equal to sigma E. Okay. So JVD is proportional to E, and so J is equal to NEVD. VD is proportional to E, right? So that's where you get your V is equal to IR, right? So J is equal to NEV. J is proportional to I. VD is proportional to E, and E dot DL is equal to V, right? So that's how you get your J is equal to sigma E, right? So NE times, the other constants from VD, right? They make up your sigma, which is the conductivity. Now, if you write it the other way, right? Instead of writing it J is equal to sigma E, you write V is equal to IR, then R is the resistance. Okay. So 1 by rho is always called the resistance, and sigma is always used for the conductance. So anything that has higher resistivity will have lower conductance. Rho is equal to 1 by sigma. So that is basically Ohm's law. Okay. Now it states that V is equal to IR, right? Now what is R? R is equal to rho L by A. The longer the wire and the thinner the wire, the higher the resistivity. So think of it like a cylinder, right? The length of the cylinder, resistance is proportional to however long the wire is. Longer the wire, more the resistance. But if you have a thick wire, it is far less resistant. So rho L by A, and V versus I is a straight line Ohm's law. Okay, so remember all this. So heat flow, charge flow is very similar to heat flow. The conductor which is good at charge will also be very good with heat. Okay, and dq by dt is proportional to the thermal conductivity and conductance, electrical conductance are related. Okay, so remember J is equal to NEV, and from that you end up with conductance, which is related to the time, time of travel, so NE square tau by M. Okay, conductance NE square tau by M, and you can then get the value for the mean free path from that. Okay, so NE square tau by M will give you sigma, and from that you will end up with. So this was a bit of a recap of the material, but we are very rapidly moving towards what we are going to do with current electricity. Okay, so having reclaimed that, what we are now going to do is we are now, we already dealt with some of this material as well with respect to the electron speed and the drift speed, which we just now introduced, right? VD, right? So now I'm ready to kind of take a moment to kind of discuss, the core principles around V is equal to IR and how to solve some of these circuits. Okay, so before that, I will quickly go over this idea of what happens in the context of in the context of mobility and charge. Okay, now the ease of motion of charge carriers inside conductors when subject to an electric field is known as mobility. Okay, so this is again they use this term mu. Okay, the drift velocity Vd is proportional to the electric field, right? So Vd, the constant between Vd and E is the mobility. Vd by E will give you the mobility. Therefore, J is equal to, so from that relationship, you can say that the mobility is E times tau divided by M, where we discussed, tau in the previous case, which is based on the mean free path, right? So mu is equal to E times tau, where E is this charge of an electron and M is the mass. So that gives you your relationship. Okay. So in semiconductors, there is two types of mobility. Okay, and we will discuss that later when we go into the details of semiconductors. There is both the electron mobility and then there is also what is called hole mobility. When we go into semiconductors, we will discuss the second idea in semiconductors because there is another current that comes into play, right? Beyond just the drift current. Okay, so now when we talk of resistance, as we already discussed, proportional to the length and inversely proportional to the area, right? So so longer the wire, more the resistance, right? So and V is equal to IR, right? And sigma is equal to NE square tau by M, right? And VD is proportional to E, right? And the constant mu, it is mu times E, and mu is E tau by M. Okay, so E tau by M, and therefore now there are many things that introduce certain non-linearities in the V versus I curve. Not every device behaves linearly. There are diodes and field effect transistors, FETs, which show non-linear relationship between V and I. Okay, these are in the realm of the semiconductors. But normally, when we think of ohm resistances, mostly speaking, they follow V equals IR. Okay, and so we typically do use V is equal to IR. But some, you look at this gallium arsenide. Gallium arsenide is a semiconductor. It has a V equals IR region, and then a non-linear region, and then a region where there is this other thing called negative resistance. Okay, so but most commonly speaking, when we think of wires, right? When we think of metal wires, we think of V equals IR. Okay, which is Ohm's law. Okay, so now I'll quickly go over this carbon resistance, but I am going to ask you to take a look at it. Okay, there is this color codes in a resistor. A resistor is a small device with connected with metal terminals on either side. Okay, now graphite resistances are there, right? Now the color coding gives you the significant figure. Now, if whether it is 10 ohms or 1000 ohms is decided by these color codes. Okay, now, black is 0, brown is 1, red is 2, orange is 3, yellow is 4, like that. Okay, now then you have this and so on and so forth. Okay? So now you have basically, it is a both a significant figure. Okay, now you have 4 bands. 4 bands, 2 bands typically represents the significant figure. Okay, then you have 2 bands which reflect the multiplier. Okay? So you have the significant figure and the multiplier. So red is 2, orange is 3, and blue is 1. Therefore, it is 23 times 10 to the power of 1. So if you have red, orange, and blue, it's 23 times 10 to the power of 1. Okay, so so that's how it is done. There are typically 4 bands, and these determine your the value of your resistance. Okay, so so remember this and learn this. Try to spend little time reading about this in your textbook. Okay, the 4 bands determine, the first 2 denote the significant digits, the third denotes the multiplier, the last band is used for tolerance. Tolerance is a measure of the correctness of the value. B.B. Roy of Great Britain has a very good wife. That is, what do you call it? It's some min, toponym, subnym, for how to evaluate this this color code, right? B.B. Roy has a very good wife. Okay, from Great Britain. B.B. Roy from Great Britain has a very good wife. So that's the mnemonic. Okay. Okay. So there is the mnemonic. And so using that mnemonic, you can then code these 4, 7, 2, and then the tolerance of how good the value is. That's a plus minus 10%. Okay, so for based on the color, right? So now as temperature increases, the resistivity also increases. Okay, and except in the case of semiconductors, which always behave differently. So they have decreasing resistivity with temperature. So because temperature increases, it is kind of like a linear thing. So 1 plus alpha, alpha is the temperature coefficient of resistance. So our rho naught is the temperature at a particular T naught, right? So now if the temperature goes to another, goes higher to T, you end up with a linear relationship, rho naught times, with which is proportional to the difference, right? So 1 plus alpha times T minus T naught. That's a linear relationship. So delta T is proportional to delta rho, right? So you see that alpha is equal to delta rho by delta T, right? Times 1 by rho naught. Okay, so 1 by rho naught, delta rho by delta T is temperature coefficient of resistance. Okay, so now different. So with temperature, your rho increases, right? For most devices except for semiconductors, where it decreases. All right. So that's as far as all this goes. The nature of resistance, etc. And then you can kind of look up these things when in terms of B.B. Roy, etc. Okay. So now we definitely need to get on with the program, and so I'm going to kind of introduce the ideas that deal with power first. Okay, so when you have an electrical circuit, right, it's all about power, right? That's why we call the company also a power company. Why do we call it a power company? Because it supplies you electrical power, right? So now, how is current and voltage related to power, right? Power is, what is power first, right? Uh, Power is the rate at which things do work, right? So right now, I have the light switched on, right? And so I have a wattage for the bulb, right? In the old days, we used to get 60-watt lamps, 100-watt lamps, etc. Now these are all called, oh my God, it's a 100-watt lamp, right? It's a 100-watt bulb. Nobody talks 100 watts anymore. Everything's low wattage. LED, that kind of low power lights. Sometimes it causes eye damage, but often LED lights is the next best thing, global warming, etc. Right? So one must be a little cognizant of that. So let me. I hope you can see my slides, right? So temperature coefficient of resistance, we already discussed, right? The battery, think of the battery like a pump, okay? Now, the battery supplies a voltage, right? And so the electromotive force V is say, pretty much similar to the potential difference, right? Or what is the battery which possesses a potential difference, V, right? Now, the potential difference is kind of related to your electric field, right? So potential difference in produces a current. Okay. Now the potential difference V times that current, V times I, is your power. It is the rate at which the battery is doing work. V times I. Okay. And because I is equal to V by R, V is equal to IR, as you know from Ohm's law, right? V squared by R is also power, or I squared R is also power. So power is V times I, V squared by R, or I squared R. Okay. So they're all equivalent because of Ohm's law. Okay. Now the EMF is not a force. Although they call it a force, it's actually a scalar, right? It is the work done on a unit positive charge to lift it from lower potential to a higher potential. Okay, so it is related to work. Power is also a scalar. Okay, so power is what? dW by dt, where W is work. Power is the rate at which work is done. Okay, so now the EMF is like voltage. V is equal to E dot dl, right? So so given all these idea, and V is equal to IR, so using these two, you end up with this term called power. Okay, the in an ideal battery, right, the potential that it provides will be constant between the terminals, but actually, because it has some internal resistance, right, it is actually a little bit less, right, than what it is, than its peak value, right? Or maybe it's even, so it's kind of, it has a rating which tells you what it is, and then it has an internal resistance which you also should know, right? So in the case of resistance, we move in the direction of current, the resistance potential decreases and increases. Okay, so an ideal battery provides a constant voltage across its terminals, but most batteries also have an internal resistance. Therefore, the voltage that it provides also, right, even the internal resistance absorbs some of the power, right? So if you have a very small resistance, right, so what is the total current, right? Total current is, let's say, the voltage without resistance is V, the total current is V divided by RL plus R, where R is the internal resistance and RL is the load, right? So if you have a full circuit, right? So now, so that is I. V divided by RL plus R is I. So now V times, or I square times RL is the power that is absorbed by RL. Okay. It's not VI. It is VI if you find the voltage across RL. Okay. So this is the power that it delivers to an external load. Okay. Internally, there is some power expended by the battery. Okay. Whenever there is current, and that is taken up by the internal resistance. Okay. So remember that. Okay. So so when you calculate power in such situations, you have to take that into account. Okay. So now when you have this voltage between the terminals of the battery, right? So there's a slight potential drop across R, and then that potential times V square divided by that potential divided by R, right? That potential square divided by RL will give you the power. Okay. So now when you rewrite the circuit, right? So I'm going to next introduce to you to Kirchhoffs laws, and one of Kirchhoffs laws states that if you go once around a loop, and any loop in a circuit, you will end up with zero voltage. So if you start from point A and you go once around the whole loop, you will end up with zero. Okay. So when you go around the whole loop like this, right, you have, and when you have current flowing in the direction of a resistance, there's a drop. So negative IR times L, negative I times little r, plus, when you go from negative to positive, it becomes plus E, where E is the electromotive force of the battery, will equal 0. Therefore, I equals E divided by R plus RL. I is equal to, therefore, the current. Okay. Now, if you wanted to find out once you know the current, I square RL is the power taken up by the RL. I square little r is the power taken up by little r, or internally used up by the battery, right? So here we have another example where you go once around the loop, right? So the current is now this way, right? So you have this one with an EMF of 2, this one with an EMF of 4. So this one trumps this one. So you go this way, it is a plus. Then you go this way, it is a minus. Plus 4 minus 2 minus I times 1 minus I times 5.3 minus I times 1.5, right, equals 0. So if you start from this point and come back here, okay, plus 4 minus 2 minus I times 1 minus I times 5.3 minus I times 1.5. So we went once round the loop, right? Should equal 0. Okay. So you go once around the loop and say 0 equals 0. Okay. So, but learn to do this quickly and learn to do it well. Okay. Learn to do it. Remember the battery signs. When you go from negative to positive, it's plus. When you go in the direction of the the current, right? Always try to go in the direction of the current, or the expected. What is that? The direction that you set by convention. Okay. You may end up with finally current being a negative value. That's fine. That means the current actually flows the other way. That's fine. You set the convention, you stay with the convention. That's very, very important when you solve these problems. Okay. So now power we define as the work per unit time, right? And as we studied, we already discussed this, right? So power delivered is E times I, right? Or V times I, right? So it is, if there is a joule heat loss, it is the amount of energy the resistance absorbs and dissipates, right? So if you look at the my electric bulb, right? What does it do with the power that it gets from the power company, right? When we say it's a 70 to 75 watts, what does it do? It converts it to two things. One is heat and the other is light. Okay, and then it absorbs some for some of the heat and some of the light you don't see, right? And so they lead to additional resistance, etc., right? So but it has a power rating, right? We already discussed 75 watts, right? uh, Now, so at a what that means is it's rated to absorb that much power. Okay, so having said that, right now we are only discussing uh, circuits which involve DC. The power company supplies AC. We will come to AC in a future chapter. Okay, but generally remember these two formulas: I square R and V square by R. Okay, so now power loss in transmission, right? So what is this power loss in transmission, right? So see, if you had to supply power to someone else, right? How do you do it, right? So let's say you run a power company, and you have a power plant which generates power. Maybe you use coal, and using coal you run a thermal reactor. Okay, that reactor produces power, right? Now you want to supply a house which is maybe 10 miles away. Okay, let's say you live in um, um, uh, let me put it, Delhi. Okay, so the owner lives in Delhi, but your power company runs in an outskirt town of Delhi, maybe I will say Muzaffarnagar, right? Or or maybe Agra. Let's say Agra, right? So from Agra, there is a wire that goes into this person's house. Let us say he lives in Delhi somewhere, uh, um, like I will say Greater Kailash, okay, or some place in Delhi. Okay. So now there's a power line that comes from Agra all the way to Delhi. Okay, that line has resistance, right? So now the longer the line, you already know SL by A, right? So and you know the thickness, right? The greater the thickness, lower the resistance, right? So there is a loss of power in the lines. Okay, so that's why they spend a lot of money trying to understand how to use power most judiciously. Then sometimes you have load shedding so that you don't have power wastage in the lines. Okay, all the time if you have to keep the power on everywhere, it costs money, costs power loss in the transmission line also. So to minimize that, sometimes they will provide 2 hours of power to farmers in the morning, and then take care of offices in the afternoon, and then houses in the night, so you can switch on your AC. Okay, if it's if you're living in August in Delhi, which is what's going on as of now, right? It's hot, it's humid, and in the night you want an AC, right? So early morning, they ship power to farmers in western Uttar Pradesh. As time goes on, they ship power to offices in Noida, okay, which is another suburb of Delhi, right? So then Later, they ship power to homes in Greater Kailash. Okay, so in the night, when you switch on your AC, you're sleeping well. Okay, so now all this in each case, right? The power plant is based in one place. We said it's based in Agra, but you're delivering power to a farm in Western Uttar Pradesh, a office in Noida, which may be making semiconductor chips, and then a home in inside Delhi, the capital, national capital region, right? So this transmission causes loss. Okay, so now if the person wants to switch on the light and experience the power, right, that power should be continuously transmitted to those areas. Okay. So enough of large lecture on what's going on here, but here we are discussing DC. In a DC circuit, if you had a long resistance, it will have a I square R power loss. Okay, so and it will absorb a certain amount of power because of the length of the transmission line. Okay, so in this case, that's why you find that transmission lines have very thick cables compared to the wire. See, I have one wire right here, right? Very thin, right? Because it's a short wire. If I had to charge my headphone, if I had to bring one wire, I would have I'd have had to bring a very thick wire from my neighbor's house. So but it's a very small wire, thin wire, but short wire. SL by A. Okay, so understand the what do you call it? The dynamics of power. Okay, so V is equal to IR, right? So here V by so you have only one resistor. So what is the power? V times I, or V squared by R, or I squared R, right? So you calculate the current and then you do one of these things. Okay, so if there is a power wattage rating on the resistor, resistors also have wattage rating. This is the maximum that they can absorb. So if they give you a resistance value and they give you a wattage rating, that means that you limit the current that you can use. You can the voltage that you can apply and the current that you can put on that resistor. Okay, so you keep that in mind, that the wattage rating on the resistor restricts your the power there. Okay, so that is the basic idea behind power. But now I'm going to spend a quick a quick introduction to the main topic that we have to discuss here, which basically deals with this idea of series and parallel resistance, and finally because we have to deal with we also have to deal with Kirchhoffs laws. Okay, so first let me discuss series and parallel resistance combinations. Although I have already a little bit discussed it in the previous class. I hope you can see my screen. Electromotive force is, as we said, is the voltage of a battery, and it is a scalar, right? And the power that it delivers is equal to is defined by V square by R, right? Now the potential drop when you go once around the circuit, it is you end up with zero. I already discussed that. That is one of Kirchhoffs laws. It's called the Kirchhoffs Loop Law. Okay, so power is the product of the current and the potential, and because V is equal to IR, it's also I square R, right? Transmission line power is dissipated to the resistance of the wire. We also discussed that, right? So now you can have elements in a circuit, right, which are used for measuring, right? There are three measures. there is a voltmeter which measures the voltage across 2 points. Okay, so you connect the voltmeter in between the 2 points and it'll tell you the potential difference between the 2 points. But again, the voltmeter, in order to produce it will have its own internal sometimes battery, right? But it can never completely not use some of the current in the actual circuit. That is, I am an observer and I am able to manage without without any observations. Hi, welcome. I will ask them to send the send this class to you, okay? Because it's a little bit late, but I'm going to continue, okay? What happened? Okay, so I'll ask them to send you also this lecture when you are, once the recording is available. Please send your email to support@jnanamarga.in, and they will send you, the YouTube link so that you can access the full lecture. Okay. So we are now discussing power and the meters that you have in an electrical circuit, right? So power is V square by R, I square R, V times I. Three different measures, and V is equal to IR, which is Ohm's law, right? Now the voltage between any 2 points is measured by this device called a voltmeter. Now, typically, you expect this voltmeter to have no resistance, to have an open circuit, but most often it will have a small resistance, and it will change the value of the current in the circuit itself during the time that you measure it. Okay. So now, if you had a potential difference VAC, and it had a very small resistance, it will then draw very small current, and then it will and corresponding to that, it will give you the value of the voltage between the 2 points. Such a meter is called a voltmeter. Okay. Now the other device that is used to measure things in an electrical circuit is this thing called an ammeter. And ammeter, it is called ammeter because of the with due respect to ampere, right? So it measures the amperage or the current. So it's a current meter, right? Voltmeter because volta, ampere, ammeter because of ampere, right? So now ammeter measures the current, that is flowing between in a particular wire. Okay, so then you also have one can also have a watt meter which measures the power. Okay, so now what I'm going to discuss is series combination and parallel combination of resistors. We already discussed this, but I want to do it one more time so that you know how to simplify it. Okay, now if you had two resistances in series, you can take it out and then you can put it replace it with a equivalent resistance. So that is what this is about. Okay, series combination and parallel combination of resistances. So what is the equivalent of a series of resistances, right? If you have two resistances series, the equivalent resistance merely the sum of the two resistances because of V is equal to IR. So if you go once around the circuit, I already said you'll get back to zero, right? So now if you go across the two resistances, it will drop I1 times I times R1 and then I times R2 also. So because of that, you can then separate the I will be common when you go in series, right? So because the I is common, you can take the I out and you can just add the R1 plus R2. So when you have two resistances series, you just sum the resistances. Now, what you must note here is what he is trying to tell you is that even though it looks parallel, because you have to follow the line, this resistance is followed by this resistance, is followed by this resistance, followed by this resistance. So what is the effective resistance between A and B? R1 plus R2 plus R3 plus R4. These are not parallel resistances, and you can see obviously if you take a careful look. So R equivalent is sigma Ri. Okay. Now, what are parallel resistances? Parallel resistances are two resistances which are tied, which have the same endpoint. Okay, so they are connected parallelly, right? The current through the two resistances are not the same, right? But the voltage between the two endpoints is the same. So V by V is the same between these 2 points. These are two resistors connected parallelly, right? V divided by I1, right? V divided by R1, right, is I1. V divided by R2 is I2. I1, when you have a junction like this, right, the entering I will equal the leaving I. In any junction, that is Kirchhoffs' other law. Okay, I equals I1 plus I2. Okay, I equals I1 plus I2. Therefore, and across these two resistance, the potential difference between any 2 points is the same. Between these 2 points is the same. Therefore, and let's call that V. V divided by R1 plus V divided by R2 is equal to I. V divided by R1 is I1. V divided by R2 is I2. So I1 plus I2 is equal to I. So V divided by R1 plus V divided by R2 is equal to V divided by R equivalent. So if you drop the V, you cancel out the V in the equation, you have 1 by R1 plus 1 by R2 equals 1 by R equivalent. So what is the equivalent resistance of two resistors in parallel? 1 by R1 plus 1 by R2 equals 1 by R equivalent, right? And if you rewrite that formula, right, if you do cross multiplication, take the LCM and all that, then you will end up with R equivalent equals R1 R2 by R1 plus R2. Okay. Now these kinds of circuits, they will draw multiple circuits like this. Like here you see what is the equivalent circuit here, right? So these two are in parallel. This one is in series with these two in parallel, right? So 1 by R1 plus 1 by R2 equals 1 by R equivalent for these two resistances. So you calculate that R equivalent, then R1 plus this R equivalent will give you the total resistance, right? So what is the current? The current is equal to VAC divided by the equivalent resistance. Equivalent resistance is R1 plus R2 R3 by R2 plus R3. Okay, so these two are in parallel. Its sequence is R2 R3 divided by R2 plus R3. You add R1 to it, that will give you the total resistance. V divided by that total resistance will give you I. Okay, so this is how you solve these example problems. There are all kinds of tricky examples. There are cases where they have infinite resistances in series, infinite resistances in parallel. We will look at 1 or 2 problems with these infinite resistances in the next class. Okay, but for now, let's look at this circuit, right? R1, then R2 plus and R3 in parallel. So the equivalent of this is R2 R3 divided by R2 plus R3. So typically when you have two resistances in parallel, the effective resistance will be less than both of them. So in this case, 20 times 3 divided by 23, that is a little less than 60 divided by 20, little less than 3, right? So it is 60 divided by 23 is what? It is 2 point something, right? 2.7 or something like that, right? So that is the resistance of these two. So 2.2 plus 2.7 will give you the equivalent resistance. Okay, so so no, but this is not 20. This is 2 ohms. Okay, so 2 times 3 divided by 5. This is 6 by 5. 6 by 5 is less than both 2 and 3, right? So now I thought this was 20. It's actually 2 ohms. That is ohm, right? So 2 plus 6 by 5 is the equivalent resistance for both together. So that is 3 and 1 by 5, right? So 8 volts divided by 3 and 1 by 5 will give you the current. Okay, and so 8 volts divided by 3 and 1 by 5, 3 and 1 by 5 is 16 by 5, right? Will give you the current. So he is saying that is 2.5 amps. Therefore, you can find the voltage, right? So now, once you find the current, then you can write what is called Kirchhoffs loop law, right? So you start from this point, you go once around the circuit. Let's go start from here. Go once around the circuit. You come back to the same point. You will have 0. Okay, so here is the circuit, right? So plus 8 minus 2.5 is the current times 2, right? Minus 6 by 5 times 2 equals 0. Okay, plus 8. So let's do it one more time. Plus 8 minus 2.5 times 2 minus 6 by 5 times 2.5 equals 0. Okay, so that's one loop around the circuit. Okay, so you can then write that, and then let's say you made I as a unknown, right? So using that, you can also calculate the I. Okay, now you can even do that in this circuit. Okay, plus 8 minus 2.5 times 2 minus I1 times 2 equals 0. And then using that, you can calculate the current in R2. Okay, so if you go once around any loop, you will end up with 0. But remember, I equals I1 plus I2. So that's why you have I1 here. Okay, so current coming in equals current going out on I1 and I2. Okay, so current coming in is I, current going out is I1 and I2. Okay, so that's how you solve these problems. So next class we will discuss these some of these circuits. Okay, so now in this circuit there is a switch. When there is a switch, initially if a switch is open, that means no current is flowing in that switch. When you close the switch, it becomes a short circuit. Then these 2 points are completely connected now. Okay, so those 2 points are connected. Therefore, when those 2 points are connected, R1 and R3 will become 2 resistances in parallel. R2 and R4 will become 2 resistors also in parallel when the switch is connected. The switch is not connected, it is almost as though the whole line is absent because there is no current flowing there. You might as well drop the whole line. So this one is 2 resistors in series. R1 plus R2 is 4 plus 8 is 12. R3 plus R4 is 12 plus 8 is 20. So then you will have this circuit. Before the switch is closed, it will be this circuit. When the switch is closed, then you have R1 and R3 in parallel, R2 and R4 in parallel. Okay, so that's how these examples are handled, right? So when you look at power dissipation, there is power dissipated in each and every resistor. You must look at the currents in each and every resistor, and you must then do I square R for each and every resistor. Okay. The power dissipation is more parallel than series combination of resistance. Okay, why is that? Like, it is because the power resistor dissipation is more in parallel combinations because you have power being V square divided by R. Okay, if the R is bigger, V squared by R is lower. Okay, now in a parallel combination, R is smaller. Therefore, V square by R will be bigger. Okay, that's why parallel circuits have more draw more power. You can obviously understand that, right? So intuitively, if you understand it, because when you connect circuits in parallel, it's supplying the full voltage to both the elements. Otherwise, they share the voltage. Okay, so V square by R is the power. So here he is calculating two resistors in parallel and two resistances in series, and then he is looking at which you consumes more power. Okay, and he is saying that the power is greater in the case of the parallel combination. So with that, I am going to close because we've run out of time in terms of the 1 hour, right? But what I'm going to suggest is that you spend some time solving some problems, go in the internet and solve some problems. Otherwise, you are also welcome to buy our application. Our application, what we have done is this month alone, we are giving a big discount up until August 15th, Independence Day sale. We reduce prices by almost 33%. So instead of 89.95, we are making it 59.95. So I advise you to consider taking a look at this. Okay. All right, folks. With that, I'm going to end. Um, and I will see you all next class for class 11 first, which will come on Saturday, and then class 12. Again, we will continue with this. We will look at a more detailed example with series and parallel resistances, and then we will look at Kirchhoffs laws, loop law, and current law, and then we will solve some problems with both involving series and parallel resistances. Maybe we'll look at infinite resistances, etc., and how to solve all these problems. So that will be our goal next time. We will not go over the previous material. I will start with the material, and I will take things forward from there, because we've already spent 2 classes with currents. So I will go through the last material in with respect to current electricity, and then we will wind down the chapter on current electricity, and then go for the next chapters. We'll slowly build up towards a crescendo with electromagnetic induction, AC circuits, and then once we've done electromagnetic induction and AC circuits, then we have electromagnetic waves, and then we will segue into other topics like modern physics, etc., before we kind of wind the material down. Okay, but that is all long way off, because the new year has just started, and our aim is to give everybody a very strong grounding. But again, students have to buy our app. They have to do the problems. Students who don't do problems don't do well in physics. Okay, you must solve a lot of problems. You must invest. You must sweat it out. And if you get the ideas correct, you must test yourself. Once you test yourself, we have now an assessment module coming up. Our app also has a self-assessment module. Use the self-assessment module. Very important to use the self-assessment module. I don't do that many problems. We don't assign problems for you, but we are going to assign problems for you in Moodle. Okay, so you join the Moodle, you look at the problems there, and then go from there. Okay, but solve a lot of problems. Without that, you're not going to do that well. You will do even better if you're already doing well. You do even better when you solve more problems, and you solve the right kind of problems. You do mock tests. Our mock test app is coming, so please get yourself ready, get yourself going, and don't think that just listening to lecture alone is going to get you there. No, solve problems. All right, I'll see you again next week.